Today we're moving on from just adding vectors and we're moving towards doing something useful with it. So the first thing that we're going to talk about is relative velocity. So imagine for this that we have a car, and as we're using our imaginations, let's imagine that it is a well-drawn car. And let's say this car is going down the street at 20 meters per second. And you've got a friend who is not very bright who has decided to Teen Wolf style ride on top of the car. No one said it was a good idea, nor do I suggest doing this at home. And what your friend is going to do is throw a ball. And from his perspective, he's going to throw that ball with a speed of 10 meters per second. So a basic relative velocity type problem would be, all right, you have a friend, you're standing on the side of the road, looking at your friend. How fast do you see the ball? So how fast do you see the ball? Moving, I guess. So if your friend is going to throw the ball with a speed of 10 meters per second and the car he's on is going 20 meters per second, you see the ball moving. You're going to add those two vectors together. So you see the ball moving at 30 meters per second. That's one easy way to look at this kind of problem. We're just going to add those two velocities together. Another type of problem, same idea. Let's say we have one car, and again, poorly drawn car, going down the road at 5 meters per second. Let's say we have another car, also poorly drawn, heading towards him at 10 meters per second. From the perspective of A, B appears to be heading at 15 meters per second towards him. So that's negative 15 meters per second. Okay. Car B looks like it's going that fast. And when we're looking at something from the perspective of A, what's going to happen what we're going to say is an observer the observer thinks his velocity, or her velocity, is 0. Okay? So, the observer, car A, is going to think his velocity is 0. So what we need to do when that happens, as A is thinking that, is to subtract away his velocity. Subtract 5 meters per second of velocity for car A. So in car A's mind, in his little dream world, and again, don't forget, poorly drawn, well, dream world, I guess it's a faster car, A's velocity is 0. And if we're in that same dream world, car B, we're going to have to do the same thing. If A is imagining himself stopped, we're going to have to subtract 5 meters per second of velocity from car B. When that happens, from A's perspective, car B is negative 10 meters per second minus 5 meters per second. Looks like he's moving at negative 15 meters per second. Relative velocity is easy. We're going to make one observer think he's not moving, and we're going to adjust the entire situation to reflect that. Or we're going to have two things stacked up on top of each other, and so we're going to add their velocities together. So it's either adjust something down to where it's not moving because observers think they don't move, or, in the case of stacked objects, stack their velocity together. That's the easy part of relative velocity. But we've been doing stuff at an angle, so we're going to have to look at relative velocity at an angle. And the best way that we have, okay, so looking at angles, looking in two dimensions, we're talking about x motion and y motion. So one important thing to note is that the x and y motions occur simultaneously. Basically, which means at the same time. And this is a helpful thing. It's telling me that for my x motion and my y motion, at least the time is going to be the same. And another really convenient thing about this is x and y are independent of each other. My x motion happens regardless of what's happening in my y direction. And so the classic way to think about this is looking at a stream problem. So imagine we have a river, and the current of that river is 10 meters per second this way. That's really fast, so don't ever cross this particular river. And if you are in a boat, and I'm going to draw the boat over here. It's a very good boat. And if you're going to take your boat and point the velocity of your boat that way, let's say the velocity of this boat, it's 15 meters per second. You have a boat that can go 33 miles an hour. If you're going to point all 15 meters per second of that boat's velocity that way, and you're going to cross, let's say a 75 meter river, point your boat across that river, two things are going to happen. In the x direction, you have the velocity of the river, 10 meters per second. And in a problem like this, we're not going to have any acceleration. It's a constant velocity of the river. And so in the x direction, the entire time you're in the river, you're going to move with a speed of 10 meters per second. In the y direction, you have the velocity of the boat, 15 meters per second. And again, your acceleration is 0. And in the y direction, you're trying to cross the river. So in the y direction, you're going to go 75 meters. So if we want to know, let's say, how long it takes to cross, that is something that happens only in the y direction. So we just need that information in order to solve it. Okay? So we'll pick an equation. And since there's no acceleration, we can say something like velocity equals displacement over time. So my time is going to be equal to my displacement over my velocity. 75 meters divided by 15 meters per second gives me 5 seconds. So I know that in the y direction it takes me 5 seconds to cross. Wonderful. So in the x direction, the whole thing also takes 5 seconds. If it takes me 5 seconds to cross, I'm only in the water for 5 seconds. And if we use delta x equals velocity times time, we'll see that I get pushed downriver 10 meters per second times 5 seconds, 50 meters. So if we look up here, while I cross in the y, I'm also being pushed down 50 meters in the x. So the path that we're going to take looks like this. My displacement is going to have both an x part and a y part to it. It's occurring in both dimensions. So my resultant displacement is going to be, yes, we're going to use the Pythagorean theorem, 90.1 meters at that angle. And I guess we're going to need to show that angle. The tangent of that angle is the opposite 50 meters over the adjacent 75 meters. So that angle, you do tan negative 1, or arc tangent of, and it's a 50, sorry, 50 divided by 75. We end up with 33.7 degrees And for what we have drawn and the angle that we are looking for, that is east of north. You're going to have to do all of those pieces. But there's one more thing we want. We also are going to need to look at the resultant velocity. I had two velocities. One of them was the boat speed of 15 meters per second. That's straight up. The other one was the river's speed of 10 meters per second. So the resultant velocity is going to be the hypotenuse of that triangle. So my resultant velocity comes out to be 18 meters per second, or very close to 18. It's 18.02. And again, we need the angle, so the tangent of that angle is 10 over 15. And that angle, when you do all your math, comes out to be, lo and behold, 33.7 degrees east of north. Okay, that's everything that we could possibly do with this type of problem. But I'm going to go one harder on you, because I'm going to go one harder on you. Sometimes we don't like to float downriver, so our goal is to cross the stream. We'll call it a river, I guess. Without floating downriver at all. We want to cross directly across our river. So we're going to say it's the same river. It has the same velocity of 10 meters per second. We have the same poorly drawn boat with a velocity of 15 meters per second. And what we're wondering is, what direction do we need to put that 15 meters per second so that the boat just goes straight across? Okay. What I want is for the boat to go straight across. I want it to follow the path of that red line. Now, common sense says, well, I'm going to have to point the 15 meters per second upstream a little bit. So in this case, my 15 meters, sorry about that, per second is the hypotenuse of my triangle. I am aiming my 15 meters per second upriver. The river is going to push me back at 10 meters per second, and my resultant velocity is going to take me upstream. So let's get a bigger picture for that whole velocity thing. And again, the boat's velocity, 15 meters per second, in this case, becomes the hypotenuse. Here's the river velocity of 10 meters per second. And again, as a note, we know we're adding these two together because they are tip to tail. And then the resultant velocity is here. So, two things that we have to do: find this angle and find that resultant velocity. For that angle, we are not going to use tangent, because I don't have the opposite side and the adjacent side. I have the opposite side and I have the hypotenuse. So we're going to use sine. The sine of this angle is 10 over 15. So that angle that we have to point ourselves into the river to go straight across is 41.8 degrees, and for what we have drawn, that's going to be west of north, or 41.8 degrees into the stream. And then the next thing that we're going to do is find the resultant velocity. This is the angle I have to point myself. The resultant velocity that we get, and this may be tricky, looking at what we have for Pythagorean theorem there, 15 squared is equal to 10 squared plus that resultant velocity squared. So my resultant velocity is going to be 15 squared minus 10 squared. So my resultant velocity is going to be 11.2 meters per second. Let me clean that up. My resultant velocity is going to be 11.2 meters per second. That is less than the boat's velocity. And think of it this way. I am having to work against the river a little bit, spend a little bit of my velocity to beat the river's velocity. That's why it's less. We're going to practice with this some tomorrow, so be ready for it.